when I got a job here at Lawrence, and I got an email from a student saying, "Hi, I know you're new. I would really like to work in your lab." And so she has been my sidekick since then. We have figured out all sorts of different ways for us to play in the lab. And along the way, good God, you presented in multiple, 2 national meetings, Grand Fellowship over the summer, the Stite Science Award. I honestly have to say, you are not my sidekick, I am yours. You have helped me. This has been a career-long goal of mine, and my career has just started because of Caren. I'm so excited for her to share this information because this is really one of the things I've always wanted to do. And the cool thing is I've gotten to watch her lead the way in doing it. So without further ado, I give you Caren Sullivan.
Thank you. Thanks, guys. So hi, my name is Caren Sullivan, and I'm here to talk to you about a spectroscopic analysis of a 15th century illuminated book of hours. And as she just so kindly put, that is my research advisor, Dr. Allison Fleshman, and also the owner of the manuscript is here, Dr. Ben Tillman, who's also been a big mentor and research advisor on this project as well. So before I can get into what a book of hours is, I'd like to go through a brief history of books in general, just so we can kind of get a feel for the timeline here. So the first evidence of any codicological work or textual evidence is in Mesopotamia. It appears in about 3500 BCE on clay tablets. However, this is not actual text, they're just symbols. And so we then see text starting to appear on papyrus in Egypt at about 2400 BCE. In about 500 BCE, parchment appears, and it just overtakes papyrus. It's a lot stronger, whereas papyrus comes from a plant, parchment comes from animal skin, so it's a lot stronger and it lasts a long time. In 105 AD, the paper revolution occurs in China. In 400 AD, we see manuscripts appear, particularly manuscripts that also have illumination and illustrations that are often called miniatures. In 860 AD, the first printed book appears in China, again on paper. The Chinese were very well versed with their paper tactics. In 1439, Johannes Gutenberg invents the printing press, or what's also known as movable type. And this leads to the first printed book of all time, which is the Gutenberg Bible. In 1639 AD, America's first printed book appears, and I believe it's on paper. And then in 1832, the cheap novel arrives. So we're going to be looking right around in here. So whenever you're presented with one of these codicological or textual works, you need to consider a few things. The first is, what is your medium? Are you looking at a clay tablet? Are you looking at something made from parchment, made out of an animal, maybe like a cow? Or are you looking at paper or papyrus? If there's writing, are you looking at symbols? Are you looking at actual language? What kind of language was used? What kind of inks were used? If there's colorants, are you looking at dyes like indigo? And here's the molecular formula of indigo. And then a pigment, vermilion or mercury sulfide. There's the crystal structure. And any codicological evidence, like I said, what language is it written in, and also if it's a theological text, are there saint names? Where do these saints come from, etc. So there's a lot of things you need to consider. So Book of Hours specifically is a small medieval devotional manuscript that was made between the 5th and the 15th century, mainly in Western Europe. And they are small, as you can see here. This is actually the one that I studied. They're made to fit right in your pocket. So they're for private and personal devotional purposes. They often begin with a calendar section. This is one we recently actually went over in my medieval class, gentlemen. And this is a calendar folio or a page from the Très Heures de Duc de Berry. It's a very elaborate manuscript, but up here you can see the days of the month will be filled in. You have some zodiac symbols up here, and actually you have a recreation or a symbol of January bringing the sun about. And then this is going to be like your first 12 pages of your manuscript. But the bulk of the text is going to contain a standard series of prayers and psalms dedicated to the Virgin Mary, and other texts may be added as well. Here we have a page from another extremely elaborate manuscript called the Book of Kells. This is what's known as a carpet page, and it would come before a prayer, or a series of prayers. And so after the Hours of the Virgin, some other texts can be added as well, but that can be up to the owner and a whole bunch of things. For instance, when the bubonic plague came around, they added an Office of the Dead section to remind themselves of their own mortality. And And so how books of hours are made is each page has like a front side and a back side, right? And so you're looking at, the front side is called recto, and the back side would be called verso, for like reverse. And so what you do is you take a whole bunch of them, and you kind of put them in a stack, and then you fold them up. It's like a newspaper. And so now you have one section of a bunch of pages, and this is called a quire, excuse me. And so this will generally be about 8 pages long, but for the calendar, you're going to have 2 sections of 6 for the 12 months of the year. And so then you take all of your quires and you start putting them together. And so the people that made these things were very organized. They had to keep them very straight and organized such that they could put them together the way that they're supposed to be. And so here is an image of our book of ours, or Ben's book of ours that we studied. And you can see it's closed, and so then you stack all of them together and then you bind them, and that's your book. So here are some images from the actual manuscript that I was studying. This is the calendar section. It's a little hard to make out, but it says September right there, and then you have your days of the month here, and then the saint names that you're going to celebrate. And then here you have the hours of the Virgin, where you get these extremely elaborate initials. You have a 6-line D, it's pretty cool. And then you have this gold leaf. And so the owner, Ben Toman, wonders, is this section, this calendar section, original to the bulk of the text? And so it's kind of interesting, just a quick visual analysis. You can see there are some discrepancies between the two. You have a much darker ink than you do in the Hours of the Virgin. You have some even degradation in the ink where all this seems to be intact. Whoever wrote the Hours of the Virgin is keeping it extremely sturdy and structured, whereas this text gets kind of a little bit wonky here. But then you...
That's a technical term.
You do have some similarities, though. For instance, the red pigment looks very similar between the 2 sections, maybe even the blue and some of the gold leaf. And so I think it's a good question to ask. Is this original or not? It's a hard question to ask. And so how can we identify materials without destroying the manuscript? So the goal is to figure out those constituents, figure out what the ink is, what kind of parchment is used, what animal did it come from, what kind of pigments or other colorants are used, etc. However, we have a requirement. You can't do any microsampling. It can't be invasive and it can't be destructive. This is a theological text and it needs to be treated with the utmost respect. So we have a few possible techniques, and I'll get into each one of these. We have X-ray fluorescence, Raman spectroscopy, and IR spectroscopy. Unfortunately, the IR that we have is too small and we couldn't fit the manuscript on top of the IR, so we cannot use that technique. So I will be talking about X-ray fluorescence and Raman spectroscopy. So what is X-ray fluorescence? Basically, X-ray fluorescence is a means to detect what elements are present and how much of that element is present. And so how it works is you send in your X-rays. It's basically like a gun, and you put it down on the manuscript, and you pull the trigger, and an X-ray comes out. A bunch of X-rays come out. And when they do that, they're going to excite those are electrons, and these are different shells. And so the higher the shell, the higher the state of energy. And so when the incident X-ray comes in, you excite one of the electrons, it goes up. So there's your excited. But now it's unstable and it doesn't like where it's at, it's uncomfortable. And so one of them is going to fall back down into that ground state, or that lowest state possible. And in doing so, it's going to release a photon. And you examine the energy difference between this photon that comes out and your incident X-ray. And that difference in energy corresponds to a particular number of electrons present, which is extremely specific to what kind of atom you're looking at, because each atom has a specific number of electrons. And so you can then determine what elements are present. And so here's an example of X-ray fluorescence that I did on the calendar in the manuscript. And I know it's a little bit hard to make out, so you have iron here on the y-axis, and then the folio, or that page number, if you recall, on the x-axis. And so I looked at each folio in the manuscript, front and back side, and what I did was I hit the blank parchment, and then I hit the black ink on that page. And so each yellow bar corresponds to the iron levels in the blank parchment, and then it has a corresponding black bar that is the iron levels present in the black ink on that same page. And so for each pair of bars, you can see that the iron levels are higher in the black bar than in the yellow bar, and then they really, really start to shoot up. And that could have been that there was some repair work done on this section, and so when they do that, they scrape some of the, they just scrape some of that gross stuff away, and so they very well could have just scraped some of those iron ions right off. And so these high iron results that we see in the ink versus in the blank parchment suggest that iron is a main component in this black ink. I also did this with the Hours of the Virgin, and I got very similar results. So this made us think, maybe we're looking at iron gall ink. And so some quick background on iron gall ink. It's arguably the most famous ink of Western history. It was used from about the 12th to the 20th century. It's a relatively cheap and easy synthesis, and it's resistant to smudging on paper and parchment because it actually binds through chemical processes rather than just kind of like being dust on top that you can just kind of brush away. And so here is an image that I took of the black ink in the manuscript using a microscope. However, there are some stability issues. It starts to break down over time, the iron gall ink, and it actually is so acidic that it'll begin to chew right through the parchment. And generally, it'll start doing it in the form, in the shape of the letters because that's where the ink is placed. But it can start to get really bad over time, and so that's an issue with it. Again, we did see a lot of that degrading in the calendar section of our manuscript, and so that was another kind of thing that was like, maybe this is iron gall ink. And so we decided to synthesize our own. We tried to see if we could recreate the ink that was within the manuscript. And so, like I said, it's a relatively very cheap and easy synthesis. It doesn't take very long, and it's really, I mean, it's kind of made out of things that are everywhere. And so you take, although there are, I looked at recipes from the 15th to the 19th century, kind of trying to get that range around where our manuscript falls. And although some of them do differ, they all have the same 4 basic ingredients. So then when I say differ, I mean you might add a few more things after. But they all have these same 4 basic ingredients. The first one being gall nuts, which are these little bits of scar tissue that form on oak trees. And then you need a solvent. You need a relatively acidic solvent though, so wine, vinegar, beer, even water will do just fine. But if you're going to choose a wine or vinegar, you need to be certain that that would have been available at the time of your manuscript. And then iron 2 sulfate is used, and that's where it kind of gets its name from the gall nuts and then the iron sulfate. And then gum arabic is used as a binder to hold it to the page. And gum arabic is basically just a type of sugar. And so what you do is you take those gall nuts and you allow them to sit in your solvent. So for my control, I use deionized water. And you allow the gall nuts to soak in the water for approximately 2 weeks with exposure to heat or sunlight. And you shake them once or twice a day. It's a fermentation process. And after that process is ended, you'll add some of your iron 2 sulfate, and it's going to take this muddy water to this absolutely jet black solution. I actually have some here, and you can come up and see it afterwards. But there's an image of it as well. And then you allow that fermentation process to recur with the iron 2 sulfate. And after that is ended, you're going to add the gum arabic once you're ready to bind it to the page. And so here is just a little chemical reaction. You have your iron sulfate, and then this, the tannin comes from the gall nuts, and then it forms the iron gall ink complex called ferric tannate, which is this huge molecule, and it's so huge that they actually are not even certain what it looks like yet. There's a couple scientists that continuously fight over what it might look like. And when you make this, you produce sulfuric acid. So that second fermentation process after adding the iron sulfate needs to be in a liquid. So here are the actual samples that I made. I have them here too. So I bought parchment from a company called Pergamena. And what I did was I contacted them prior to purchasing, and I asked, how close are your chemical processes of treating this parchment to actual medieval processes? And they got back to me and they were like, pretty darn close. Like, we try and do it exactly how they did it. I was like, oh, that's cool. So I went ahead and I purchased calf parchment. The reason being, it was another visual analysis. Deer parchment is really dark. Goat parchment has a bunch of speckles on it, and so I just tried to get the one that actually looked like our manuscript, and so I went ahead and purchased calf parchment. And then I took my ink and I made these little strips on it, kind of trying to recreate the width and depth of the actual ink that was in the manuscript. And then I thought about, we might have some surface problems with this and how far down the ink goes to make sure that you're looking at ink and not looking at parchment. And so I went ahead and I took one piece of parchment and I just dyed it completely with the iron gall ink. And so now we know that iron is a main component in this ink, but we don't know how anything is bonded together, how these atoms are actually bonded together. We just know what atoms are present. And we also wanted to compare the manuscript to the samples that we made. And so how can we do this? We need another technique than X-ray fluorescence. We need something more. And so we decided to start utilizing Raman spectroscopy. And so here's an image of the manuscript underneath the confocal of the Raman, which is the microscope I actually took that image with that I showed you earlier. And so you need to have the manuscript in this little apparatus, and it's in it right now, to keep it secure and such that the binding it doesn't break or anything. It has to be open to an appropriate angle, and also to make sure that you're taking a spectrum of actually what you think that you're looking at. Okay, and so I'm going to get into Raman spectroscopy now. So it's a spectroscopic technique, and so where that confocal comes down, a light source comes out of there, and it's actually a laser. And you can control the frequency of that laser, but you need to have multiple lasers. And so basically what you do is you're utilizing a light source to talk to the vibrations within your sample. And so each pair of atoms is bonded, and they're going to move. And they're going to move at a particular frequency. And so here we have a carbon atom and 2 hydrogen atoms, again represented over here. And these are just 2 of the many formations in which these can vibrate. And for Raman spectroscopy, we'll be mostly looking at this where it's symmetric vibrating, where both are moving at the same time. And so the C and the H are bonded and they vibrate at a particular frequency that is particular to the carbon being bonded to the hydrogen and the way it's moving. And so from this, we can start to look at, okay, how are these atoms that are present actually bonded to each other? And so here's like another example of how it actually works. So here's your sample, and you're going to send in an incident light or frequency, just like you sent in that incident X-ray with the X-ray fluorescence, but this time we're using a laser source. 99% of that light is going to bounce off the sample at the same frequency that you send in. Actually, it's more than 99% of the light, and this is called Rayleigh scattering. However, in the 1930s, a man named C.D. Raman noticed that a very small fraction of the light is bouncing off at a different frequency than the incident frequency. And it's actually 0.00001% of the light. It's such a minute amount of the light is doing this. And it's generally at a lower frequency because some of that energy was lost into those vibrations. And so what you do is you look at the difference between this frequency and the Rayleigh frequency, and you look at the shift between the two, and this is known as the Raman shift. And that shift is going to be particular to the frequency of those vibrating atoms, vibrating molecules. So here's an example of when Raman spectroscopy works beautifully, okay? This was work that I did over last summer where I was looking at the red pigment in the manuscript, comparing between the calendar and the hours of the Virgin. So I'm looking here and up here. And so in pink, we have the spectrum of the calendar red pigment, and then in the purple, we have the spectrum of the hours of the Virgin red pigment. And as you can see, they're pretty similar to each other. And so what you do is you go into a literature database, which is a whole mess of Raman spectra. And you kind of have to search around, and so I thought, hey, maybe this is mercury sulfide or vermilion. And I looked up a spectrum of vermilion, and this is what I got. And so it's a qualitative analysis, and you compare the location of the peaks, and it's pretty definitively vermilion. This red pigment in both sections is mercury sulfide. However, you can see that some of the peaks, they don't quite line up, and that can be the way that what it's bound to as well. And so with this spectrum, this was going to be pure mercury sulfide, just looking at like the powder, whereas I'm looking at mercury sulfide that's in a binder bound to parchment, and so the vibrations are going to be a little bit different. Okay, that's when Raman spectroscopy works wonderfully. But sometimes we have problems, and the problems come from fluorescence. And fluorescence is not always a bad thing. It's a bad thing in spectroscopy, but it's what gives everything its pretty color. And so And so what you do is you send in your light and your electrons. So this is an energy level diagram, and here you have vibrational states, and then these big guys are electronic states. And so you send in a photon, and the electron gets excited, and this is called absorbance. And then some of that excited electron is going to fall back down, and that's vibrational relaxation. And that does not release a photon. It's called non-radiative decay. However, you can have this thing called fluorescence where it goes between an electronic transition, and in doing so, it releases a photon. And you can also note that this fluorescence occurs at a lot longer time range than the vibrational relaxation and even than the absorbance. So it begins to overwhelm that already very minute Raman signal. So if you recall this diagram, you have your instant light going in, your Raman, and your Raleigh. But now we have fluorescence. And so it's completely overwhelming the detector in the Raman. There's all of these photons hitting everything, and that little tiny Raman signal is completely lost. And so this is what it looks like when you have fluorescence in your spectrum. Instead of coming back down again, it just continuously goes up and up and up. And so, like, you might have a few peaks around here and around here, but you can't be certain of that. You can't be certain that those are peaks and not just little bumps of noise. So we need a way to get rid of the fluorescence. So here's a spectrum of iron ball ink in solution that was in a paper by Kurowski, and they purchased their iron ball ink from the Art Institute in Chicago. And so this is a very nice looking spectrum, how it comes back down. And so here you have a couple of peaks noteworthy: 1482, 1333, 1275, and 562. And so we decided to set out and look for one of these peaks. Let's see if we can find it in our spectrum. And so Stephen Bell, this wonderful spectroscopist, came up with this beautiful way to eliminate the fluorescence without buying another laser, without buying any other equipment. And it's simply a data manipulation technique. And so here again is your fluorescent spectrum, crazy going up. And so it's called shifted subtracted Raman spectroscopy. The reason being, you're going to take your spectrum, you're going to shift it over, you're going to subtract that shifted one from the original, and then Raman spectroscopy. Okay, so here's another little cartoon of how it works. And so what you do is you go and you take a spectrum at the origin, and what I mean by that is you just sit down and you collect a spectrum like normal. And then you're going to shift over ever so slightly. So imagine that I have a little ant on my shoulder, okay, and I take a little step. Now I didn't move very much, but the ant is like, whoa. The ant moves like a mile, okay? And so I'm the fluorescence, the ant is the Raman peak. The ant moved, I didn't move much. So the fluorescence remains relatively unchanged while that peak actually moves. And so then what you can do is if you subtract that shifted spectrum from the original, I go away. And how the ant has changed is left behind. And I say how the ant has changed because, gosh darn, doesn't that look like a derivative? And you can treat it like a derivative. And so you fit it with a mathematical equation. You fit your derivative-like, is what they call it, spectrum. And then you decide to look at only the positive components. You integrate. And what you do is you get your peak back that was hiding under here. Now these have been a little emphasized, okay? But that peak that was originally hiding under here, now he comes back down like he should and doesn't keep going up and up and up. Now you know that that peak is there for sure. So going back to, this is my spectrum of the synthesized black ink that I created on the purchased parchment that we bought. And it goes up and up and up. And like I said, you know, maybe we have something there, maybe we have something there. And the Kurowski says, look for these peaks at 562, 1275, 1333, and 1482. And so we did scissors and, well, I'm sorry, shifted subtracted Raman spectroscopy. It's also called scissors. Yay. Don't take scissors to the manuscript. And so we decided to look for one of these peaks, and this is what we found. This guy is hiding at 1335, which is pretty close to 1333. And it's actually close enough that it's kind of one and the same peak. Because remember how I said that you're looking at those vibrations and that frequency can change a little bit depending on how things are bonded. And so you have to but you have to fall within a range. You have to fall within an appropriate range. And so we were able to find this 1335 peak in my, my control that I created. So we went hunting for it in the manuscript. And this is what we found. So here's the fluorescing spectrum of the black ink on a folio in the calendar. And then here's the black ink in the Hours of the Virgin. There are peaks hiding. So here's the 1333 hiding here. This one's a little bit easier to see actually in the original spectrum, 1337. And so that one peak that we were looking for is there, which is pretty cool. And so my results, going back to not only this peak, but the fact of how high those iron levels are with the X-ray fluorescence in the ink, iron is definitely a major component in that ink. And so then we look at the peak. And so comparing to literature, so here's mine, 1335, the Hours of the Virgin, 1337, and the calendar, 1333. And then Kurowski said, 1329 to 1344 for iron gall ink on paper. He was looking at paper. And then they were also looking at gallic acid, which would just be the gall nuts. The gallic acid is produced by the gall nuts in solution. And so that appears at 1336. And then even another paper, Lee, they looked at the regime between 1310 and 1350 and said that those peaks are significant to iron gall ink. And so another thing to take into account is the resolution of our Raman, which is 2 inverse centimeters to 15 inverse centimeters, depending on how long you expose the laser. So depending on how your acquisition time, so how long you expose it, and then how many accumulations that you do. And so I tried to maximize that as much as I could, such that my resolution was so small. So I do fall within this regime. So we were able to find this one peak that was hiding. Now if we return to the original question, is this original to this? I don't know. I don't know if anyone will ever know. There's a lot of questions that go into this thing. There's so many questions. And this is just the beginning. But it's a really interesting project. And so, there we go, future work. The next thing to do would be to go ahead and try the shifted subtracted Raman spectroscopy. See if you can find those other peaks that Kurowski was talking about. See if all 4 of them are there. Then maybe we can get closer to saying, yes, definitively, this is iron gall ink. We'd like to determine what other pigments are present. Like I said, I was able to look at the red pigment, but the blue pigment, the gold leaf, what is that blue pigment? That would be a really cool project. The biological work on the parchment, did it actually come from a calf? We actually have a student, Brianna, who's going to work on it next year. There you are. And that's her big question. I think that's another road you can go down, There's so many ways. And then, of course, you can go ahead and perform all of these processes with another work of art. And so this project is huge, and so I'd like to thank a lot of people for all of their time and all of their help with everything that happened. So obviously my research advisor, Allison Fleshman, my other research advisor and the owner of the manuscript, Dr. Ben Tillman, thank you for letting me examine this. The stacker manager, Danielle Martin, thank you. There you are. And thank you, Lawrence University, for the Stites Fund and the Scranton Fellowship. Thank you to that family. Helpful professors, Jay Stork, he was the one who said it's not going to fit on the IR, it's not happening. Andrew Knutson, the geologist, taught me how to use the X-ray fluorescence gun. That was pretty cool. And obviously Dave Hall for all of his help with my presentation. And then previous students that worked on this, Allison Peregrine and Marty Allen, they did fantastic work. And obviously my awesome friends, all of you guys that are here, and special shout out to Julia and Nico, of course. Thank you. You guys have any questions? Yeah.
So is there any chance when you're working with that is there any technique that you could get a false peak to emerge because of noise?
Yes, and so that actually did happen to me once. And the way that you can really tell that is if you're, when you shift the spectrum, if that peak does not shift, it's not a peak. It has to shift. If it doesn't shift, and that's, I had a lot of trouble with that, yeah. Because there was one where I collected noise and I was like, that's a peak, and it wasn't, because it didn't move, it never moved. Yeah.
You used the scissors technique because fluorescence was swapping out the Raman signal.
Mm-hmm.
But you were really looking at the Stokes shifted Raman spectrum. Can you look at the anti-Stokes shift, the higher energy Raman?
I haven't tried, but I do know that, I did say when I was talking about Raman spectroscopy that generally the frequency is lower because some of that vibration is lost. And so when it's lower, that would be your Stokes. And so anti-Stokes would be if you're able to excite the electrons instead of watching them come back down. And that's a lot harder to do because the electrons don't want to be there. But I don't know.
So the fluorescence would still be there because of the wavelength of the laser.
Okay, so yeah, since the fluorescence is dependent on the wavelength of the laser and independent of what's going on with the rock, then it would, yeah, I guess it needs to be.
Ah, okay.
Yeah.
Can you go back to the graph of the amount of iron on the parchment, the yellow and black bars?
When you say graph, I totally know what you mean. Bar graph.
Not my kind of images.
Once upon a time. Before I know. There it is. A million times.
Do you mean, so there's this sort of, I see a pattern where there's higher levels of iron on the parchment, on the long parchment, towards the front of the photo, on the calendar.
Right.
And then it sort of reduces, and then there's, do you have any, could you talk about sort of, speculations about why that would be that?
It could have been when they were scraping it off. Maybe they scraped it off and they scraped it right onto the parchment. And maybe they're just sitting there. And because we don't, clean this thing, it's just, they're still there. That, I don't know. It could be that. It could be that when they were scraping it and they were trying to make it look nice, maybe there was some iron in whatever they were using to go over the parchment. But I don't know. I think that's a good question.
So it's some sort of contamination on the surface of the parchment?
Yeah.
No, okay.
Yeah, I would think so.
Well, what other compounds? You didn't just look at iron, you looked at,
I looked at copper too.
and,
Well, I looked at mercury.
and lead.
Yeah, really high level.
High levels.
Really high level.
If you touch it, wash your hands after.
Yeah. It's just a bag, wash your hands. Yeah, the lead levels, we're still not really sure, but we did reach out to a woman, Abigail Plant, at the Walters, right? Yeah. And she's this wonderful woman. Oh my gosh, she does so much work on all these manuscripts. And so we reached out to her and said, you know why? Like we might have all these high lead levels, crazy high lead levels. I'm scared. And she said, well, when there was some repair work done to this manuscript.